Hey guys, this video series I'm going to show you right now is just going to kind of deal with how a neuron is able to generate an action potential. It's one of the more complex ideas in the nervous system. I'm going to play a little video here that's kind of going to go over the process and explain to you the basic mechanism at which sodium and potassium move across the membrane. Those are the two chemicals that we're dealing with that are vital, or we call them electrolytes that are vitally important in order for a neuron to generate this particular action potential. So just kind of pay attention as this video goes on, and I'll talk a little bit more about it as it happens.
Potential is a really good example of this. It might look pretty complicated, but all you need to know is how diffusion and active transport moves ions. This is the structure of a myelinated neuron, and if we look closer at the axon, we can see that when the neuron is at rest, there is a higher concentration of sodium ions outside the cell compared with the concentration inside, and it's vice versa for potassium. Because of the concentration gradient, an active process is needed to maintain this situation, the sodium-potassium pump. This uses energy in the form of ATP to move the ions against their diffusion gradient.
So remember, during this component that you're looking at right here, guys, you have the sodium-potassium pump is running in this actual neuron itself, and it's going to bring in 2 potassium and kick out 3 sodium. So it's continuously doing this, and this is moving things against the concentration gradient. So when a neuron is at rest, okay, when a neuron is at rest, we call it being polarized. There's more sodium on the outside and more potassium on the inside. But because there's a greater amount of sodium on the outside, okay, there's more positive charges on the outside than there are on the inside. Both sodium and potassium are positively charged, but there's more positive charges on the outside than the inside. So the outside has a positive charge, the inside has this negative charge.
And this gives us resting potential in the neuron, which is about minus 70 millivolts, and it's said to be polarized. Now we're going to look at what causes the pattern of changes in membrane potential when the neuron fires. Looking at the soma of the neuron, we can see the dendrites. This is the site of synapses with neighbouring neurons. The impulses received are processed. So
these dendrites here are going to become stimulated. If this is a sensory neuron, this can be something like pressure. Light could hit the end of this thing. You have some type of receptor that's going to stimulate this neuron. And this stimulation then is going to cause this influx of sodium ions to occur. And this is going to occur at this area here called the axon hillock. And this is going to travel down the whole entire axon that you're going to see when we go through depolarization.
Small amounts of depolarization spread to the axon hillock. If this small amount of depolarization reaches a threshold, it causes voltage-dependent sodium channels in the axon membrane to open. Sodium ions diffuse along their concentration gradient.
So now what's happening here is these sodium channels are opening up, okay, as a result of this stimuli that's occurred. These sodium channels are going to open up, and now sodium's going to come rushing in. The reason that sodium's going to come rushing in is because, remember, this sodium-potassium pump right here was kicking out 3 sodiums to begin with. So now you have all this sodium that's out here, and things like to move from an area of high concentration to low concentration. So now all this sodium is going to come rushing down into the cell. We're calling this depolarization now.
Into the cell, causing the inside of the neuron to become positive compared to the outside.
So now the inside of the cells become more positive, the outside's becoming more negative.
This stage is represented in the uphill part of the action potential trace. The depolarization from the soma reaches threshold and opens the sodium channels, and this allows a rapid influx of sodium ions. This stage of the action potential is called depolarization. Looking back at our neuron, the sodium channels are now closed, and potassium channels will allow potassium ions to diffuse out of.
So now the opposite is going to happen in repolarization. These potassium channels are going to open up, potassium is going to leave, and now the outside is going to start becoming more positive, the inside is going to start becoming more negative, as you have all this influx of all this potassium making its run out.
This swaps the polarity of the membrane again, so that the inside is now more negative than the outside. And we can see on the graph that depolarization generally reaches around plus 40 millivolts before these potassium channels open. As potassium ions diffuse out, this causes repolarization of the membrane, as the inside becomes more negative again. Potassium channels open and close very slowly, meaning that too much potassium diffuses out, resulting in hyperpolarization. This is then
So during hyperpolarization, what's happening is we have so much potassium that's running out that it goes beneath that original resting point that it was at. So therefore, we're going to have to fire back up the sodium-potassium pumps to return things back to normal.
Because sodium and potassium leak through the membrane. This is by diffusion with their concentration gradient. The sodium-potassium pump also helps. This brings the membrane potential back up to the resting potential. And you can see this in the graph too. In the final part, potassium channels close and the hyperpolarization is corrected. This restores the resting potential. The time when the membrane is hyperpolarized is called the refractory period, and during this time no action potential can occur. And this also means that the action potential always travels in only one direction. Remember, we have been looking at only a small section of the axon. The nerve impulse is propagated because these events occur repeatedly next to one another. The depolarization during the early phase of the action potential travels along the next part of the axon. This opens voltage-dependent sodium channels, and the process repeats. This is how the impulse is passed along the length of the axon. Remember also that in a myelinated neuron, like the one pictured here, action potentials only occur in the nodes of Ranvier. These are areas where there's no myelin insulating the nerve, and it produces faster...
Remember, these nodes of Ranvier are only found in neurons that are associated with the peripheral nervous system. These are the Schwann cells that are producing this myelination, and this is where this influx of this sodium-potassium occurs in these particular neurons themselves.
The action potential is really simple. All you need to understand is diffusion.
So that video kind of explains the whole entire process of how this neuron is able to generate this action potential. Remember, once it reaches the end of the axon, at the axon terminal, that's where those neurotransmitters are going to be released, and then the next neuron is going to become stimulated by those particular neurotransmitters. This is one of the more complex topics there that we talk about in here. Make sure you watch this video again and again and again until you really grasp the concept as to where it's moving what and those particular different times of an actual neuron generating this electrical impulse.